Hello, friendly people. This is Dr. Benton, and today we're going to be moving on to our next standard about the weather. We're going to be talking about the relationship between air pressure and weather fronts and air masses and tornadoes and thunderstorms. And this is where we really get into what is weather and what causes weather. So our today's lecture is about humidity. And so first warm-up question, what is humidity? And this is a meme my wife picked out for us, because we both have curly hair. And if you're a girl, you probably understand this. If you have curly hair, you probably understand this. For all the boys out there, humidity makes curly hair go crazy. So weather we talked about already in depth. We said that heat causes low pressure, so this L is not for low temperature, this L is for low pressure. It's red because of the temperature. Red is hot, blue is cold. Cold makes high pressure. Red makes low pressure. We said that those are two of the main things that we talk about with weather, temperature, pressure, wind, but we also talk about humidity and precipitation and clearness or cloudiness. So today we're going to learn what is humidity. This is a concept that's kind of advanced. Last year I didn't teach it because the year before I had a lot of trouble with people understanding it. So for these first few slides, if you don't understand it, that's okay. If you do understand it, great, you're smarter. What I really want you to try to pay attention to is the principle, and we're going to review that scientific principle at the very end and talk about how it's going to relate to the rest of this weather stuff. So first, what is humidity? Humidity is the relative amount of water vapor in the air, and typically we talk about an relative humidity. Because while absolute humidity is interesting, that's the total amount of water, that doesn't really matter as much because the amount of water that can be held changes with temperature. And so we talk about, of all the water it can hold, how much of it is it holding and how much of it does it still have left to fill. If we have 100% relative humidity, that means that it's full. It can't hold any more water. The air is completely saturated. There's no more evaporation. And in addition, if we tried to add any more water to the air, it would condensate into a liquid. There is no more space for water vapor. On the opposite end of the spectrum, 0% humidity, there is no water vapor in the air. Water evaporates extremely quickly under these dry conditions, and even in the deserts of the world, we still don't hit 0% relative humidity. We hit 100% humidity all the time, though, and that's because the air doesn't hold a ton of water. And so a lot of people get confused. They think, oh, 100% of the air is water. No, this is not how much of the air is water. If the air was 100% water, it would be an ocean and we couldn't breathe it. In this case, we're talking about how much of the bucket is full. So if you imagine the air like a sponge that can soak up water, is the sponge dripping wet 100%? Is the sponge completely dry 0%? Or how much water is the sponge holding and how much more can it absorb before it starts dripping? That's what we're talking about here. And that varies. The sponge, the size of the sponge, I guess, varies depending on temperature. Warm air holds more water vapor. Cold air holds less water vapor. So the warm air is kind of like a bigger sponge. We see this kind of exemplified here. The same amount of water, 6 ounces, 6 ounces, 6 ounces. But if I get a bigger glass, I can hold more water, right? So the relative humidity here is 100% because the glass is full, but here it's only 2/3 of the way full, 67%. Here it's only half of the way full, 50%. That's why relative humidity isn't as good of an indicator for the actual amount of water in the air, is because relative humidity does vary depending on temperature, and temperature fluctuates every hour of the day. The important thing to remember, though, is that it changes. As the air gets warmer, the relative humidity is decreasing because it can hold more water. Because it can hold more water. In the opposite direction, though, as it gets colder and colder, the amount of water it can hold decreases. And so eventually, that percent humidity will reach 100%. And when it hits 100%, we call that the dew point. The dew point is the temperature at which air cannot hold any more water. Relative humidity 100%. So if the dew point is 65 and the air temperature is 65, we know that that's how much water vapor it can hold. It cannot hold any more. But notice that even as the air temperature increases and we can hold more and more humidity, more relative humidity, the dew point is staying the same because that dew point is the best indicator of the actual amount of water vapor in the air. So we use dew point as an indicator of the actual amount of water in the air, the amount of water vapor. And that is something that does not vary with temperature. What varies with temperature is whether or not we are at that dew point. Once the temperature hits that dew point, if it tries to go under that dew point, the water can't evaporate anymore. It actually does the opposite. It condensates out into a liquid. If we go above the dew point, then we are able to hold more. It actually increases the evaporation. So the dew point has to do with the actual amount of water vapor that's in the air. The dew point is 100% humidity. So if we continue cooling the air past the dew point, what will happen? It can't hold that water vapor. It literally spills out. And we call that condensation. When it happens on a surface, we call that dew, like on grass. And so that's where I think the name dew point comes from. The dew on grass is the temperature at which we have dew, the dew point. And so the main point here is that the temperature affects the amount of water vapor the air can hold. If it gets warmer, it can hold more water vapor. But if it gets colder, then the water actually comes out of the air. The water vapor is removed and it becomes liquid condensation. So that's the part about humidity that's kind of difficult for people to understand. What is humidity? What is dew point? If you don't understand that, that's okay. This is just background knowledge to make you smarter. As we move on, though, this is the important part. This is the part we need to know for our test, for the standard. So when do we reach the dew point? Now, on the previous slide, we said that the ground naturally gets colder at nighttime because that has that low heat capacity. So, yeah, we find dew on the grass all the time, but what about in the air? Well, the air actually gets colder as we increase our elevation. As altitude goes up in the troposphere, it gets colder and colder, specifically about 3 degrees Fahrenheit for every 1,000 feet. So if you imagine if it was 90 degrees at sea level, it drops to 78 degrees at 4,000 feet. Up around 5 miles, we're down to 30 degrees. And the troposphere can extend up to about 10 miles, so it can get very, very cold the higher we go. It becomes freezing the higher we go. What that means is that as the water vapor continues to lift, it will reach that dew point. It will reach that dew point where it will condensate and form a cloud. So that's the easiest way to make this condensation. That's the easiest way to meet this dew point, and that's exactly what happens to make things like clouds. So what makes that hot air rise? Well, we've been studying all year that hot air rises because hot air is low density, warm air is low pressure, and low air pressure rises. That low air pressure, that warm air, has already got a fair amount of moisture in it. One, because of the temperature, it has a low relative humidity. It can hold a lot of moisture. And the heat that's causing this low pressure is the same heat that drives evaporation. So we have more evaporation, we have more capacity to hold water, and then we bring all that moisture up with the rising air where it cools. It condensates, those little microscopic droplets of condensation form clouds, and those clouds will rain back down because liquid water can't stay in the air for very long. So what we see in the middle of a low pressure area, the middle of a low pressure system, the middle of a low pressure air mass is clouds, is rainy weather. We're going to learn more about air masses tomorrow, and we're going to learn more about things like hurricanes that are centered around low pressure areas, because it's the low pressure areas that create the clouds as the water vapor cools when it rises. High pressure does the opposite, though. High pressure sinks. The air gets cold up high, and so it travels downwards. It sinks because it's high density, high pressure. Once it comes down, though, it actually warms up a little bit, because the ground is warmer. If it gets colder as we go up, it gets warmer as we go down. And as it gets warmer, we decrease the relative humidity, we increase the amount of water vapor that can be held, and we're making it easier for the water to evaporate. We're making it less likely to condensate. So what that means is that in a high pressure area, the clouds actually disappear. That water vapor stays evaporated, and that condensation evaporates. The clouds evaporate as they come closer to the ground. And so in high pressure systems, we have clear skies, sunny skies, we have good weather. And you might have noticed that this winter, when we had the cold spells, it might have been a little stormy to begin with, but then it stayed cold a few days and we had sun, clear skies for a few days. Once those clouds came back, though, it warmed up a lot, and that's because the heat was what was causing those clouds. So the takeaway: high pressure air is colder. High pressure air is colder, it rises, it creates calm, clear skies. And that's what we see on this weather map. Remember, the H is for high pressure, the blue is for cold, and we see not a lot of clouds here. Good weather. Low pressure air is warmer. That's why we have the red L. It's warmer, it's lower pressure, that water vapor is rising and condensating, and that's why we see so many clouds. These fronts are actually the borders of the air masses, the directions they're moving. We're going to talk about this for the remainder of the week as well. But the principle: low pressure storms, high pressure clear. We also see that in this 7-day forecast. When the temperature rises, that's when the rain comes. When the temperature falls, it becomes higher pressure. That's when we have the clearer days. So again, really look for this the next time you're seeing weather on TV or looking at a weather map. In Georgia, we tend to see this especially in the winter time, because during the summer it's so hot that the clouds actually cast shade, and that affects the temperature. But during the winter, we don't have that same effect. During the winter, it really is all about this high pressure, low pressure interaction. So take it out the door. Now that we've learned which air pressures have better weather, I want you to tell me which air pressures do have better weather and why. And this is also my wife's favorite singer, Dolly Parton, and a quote from her: "The way I see it, if you want the rainbow, you gotta put up with the rain." And that's saying sometimes good things only come out of bad times. And I think that's very fitting for now. I'm going to upload another YouTube video, another Edpuzzle video, which is a compilation of YouTube videos. These are the big four. This is also a website I wanted to show you. It's about Marietta's humidity and weather in general. Let's take a look at that real quick. Good. So this is talking about the average yearly weather in Marietta. We can zoom down to things like humidity, but it also talks about precipitation and other things. It defines humidity pretty well for us, and it tells us that the best way to perceive that humidity is through the dew point. And that's what this map down here shows us, this graph. With the lower temperatures, it feels drier. When the dew point increases, we have a lot more water in the air, and it's harder for that moisture to evaporate, so the sweat sticks to us. It's sticky, it's miserable. We feel coolest when the humidity is low, when the dew point is low, because that evaporative cooling works more efficiently. So in the deserts where they have a dry heat, it can get over 100, but it actually feels pretty comfortable because you're allowed to evaporate more. In the south, when our sweat doesn't evaporate, that's when we feel miserable. And we see that in Marietta, that tends to happen 82% of the time here in July. 82% of the time, it's either muggy or oppressive here in Marietta. During the winter months, though, we don't have a lot of moisture at all. It's dry, it's comfortable. So for those of you who've lived here your whole life, you kind of take these weather cycles for granted. If you ever travel across the country, maybe up north, maybe out west, see how this changes. See how different humidity levels affect your comfort. Closer to the coast, it is more sticky because it is more humid. It is more higher dew point. Out in the desert, lower dew point, it feels much more comfortable. So I hope you enjoyed this little lecture. Please send me any questions you might have, and tomorrow we'll talk about it some more when we talk about air masses. Thank you.